Okay, so welcome back to Lewis diagrams and shapes part 2. So this is the Lewis diagrams and shapes that typically you'll come across for level 3 now. And for level 3 you move beyond 4 electron clouds, which was the restriction for level 2, and we move on to 5 electron clouds. So if we're dealing with 5 electron clouds and 6 atoms, then a good example to do the Lewis diagram for would be PCl 5. So we're going to cover the Lewis diagram in each case. We're going to cover the number of electron clouds from 5 to 6 electron clouds at a maximum, and then we look at the molecular shape and decide whether the molecule is polar overall or not. So for PCl5, just again to go through the method for drawing Lewis diagrams, you want to determine the total number of valence electrons. So for phosphorus we have 5. For chlorine we're going to have 7 times 5, so that's going to be 35. So in total we have 40 valence electrons to arrange in the Lewis diagram. Put the first element typically in the compound in the middle, and then just arrange 5 chlorines around that. Now again with the chlorines, just with bonding electrons, just use lines. This becomes, the point I made in the level 2 video becomes more apparent now that we have so many different atoms involved that if you use electrons, if you represent electrons with dots all the time, it becomes quite messy. So for the bonding pairs we just use lines, and then make sure you put your lone pairs in on every single one of the chlorines. So each of the chlorines will have 3 lone pairs. Now the interesting thing which arises here for the first time in level 3 is this idea of an expanded octet, because if you notice the phosphorus has 2, 4, 6, 8, 10 electrons, 10 valence electrons, which means it has an expanded octet. And an expanded octet is only possible for row 3 or energy level number 3 because of the 3d orbital, which can accommodate up to 10 electrons. Also, because the 3d is quite close in energy to the 4s, that can also accommodate another 2, which will be apparent in compounds with 6 electron clouds around them. But for phosphorus there's 10 electrons in the valence shell, and as a result it has an expanded octet. This shape we have here is a new shape as well. It's called trigonal bipyramid, or trigonal bipyramidal, B-I-P-Y-R-A-M-I-D-A-L, trigonal bipyramidal. And to draw this shape, what you're going to have here is you're going to have a phosphorus atom in the center. You're going to have 3 chlorine atoms which are in the plane of the page. And then you have 1 chlorine atom which comes out towards you. So that's using a wedge, make sure you fill it in. And then 1 chlorine which is going away from you. Alright, the bond angles here between the 2 chlorines which are in the plane of the page, that's going to be 90 degrees. Between the chlorines here, that's going to be 120 degrees. And the overall shape is essentially 2 pyramids which are sitting base to base, so trigonal bipyramid. And if I try to highlight that here, so there's 1 pyramid right there, and then the other pyramid sits down here. So that's a trigonal bipyramid. To talk about polarity, so my diagram is going to get a little bit more complicated. I'll use a green arrow here. There are 5 of these polar bonds in phosphorus pentachloride, but each of these polar bonds are pulling in opposite directions away from the central phosphorus, which is not as electronegative as the chlorines. So because all the dipoles cancel, the electron density is symmetrical, so you have symmetric distribution of electron density, and as a result the molecule itself is non-polar. So that's PCl5. Just to take a look at what PCl5 looks like in FET. So I'm using FET here just like I did in the level 2 video. So if you remove all the atoms, and what we had there was trigonal bipyramidal, so we had 1, 2, 3, 4, 5 bonds to the central atom, so 1, 2, 3, 4 and 5, with no lone pairs. So if we look at the molecular geometry, it's trigonal by pyramidal. If we show the bond angles, you can see the 120s there, and if I move it around to just let it settle, you'll see that it settles with bond angles of 90 degrees then as well. So it should be 120 and 90. So we just get it to arrange itself the right way there. There we go. So 120 for the big angles, and then 90 for the smaller angle between the chlorine and the phosphorus itself. So FET is quite useful for visualizing these molecules in 3 dimensions, something that we can't do in 2D. So that's for 5 electron clouds and 6 atoms, and that was trigonal by pyramidal. Now, if we take a look at the next situation, which is going to be 5 electron clouds and 5 atoms. So a good molecular example of this is SF4, sulfur tetrafluoride. And in this case you have 6 electrons here, 4 times 7 for the fluorines. That gives you a grand total of 34 valence electrons. So the Lewis diagram here is going to involve sulfur being at the center. You have a bond with the fluorine here. You have a fluorine coming off here, another one here, and the 4th fluorine comes out here. There's also a lone pair of electrons on the sulfur, and then each of the fluorines have their own three lone pairs. And that should add up to a total of 34 electrons. Just stick them on there. This shape, again, we have an expanded octet situation because you have 2, 4, 6, 8, and 10 electrons again on the central atom, which is an expanded octet, and we already explained that for phosphorus pentachloride in the first example. Expanded octet. This shape is called a seesaw shape. Seesaw shape because it looks like a seesaw. So what you have here is you have sulfur in the center, which would be the pivot point of the seesaw. You have one leg of the seesaw here coming out towards you. You've one leg going away in the background, and then you have the seats essentially of the seesaw coming out to the sides. So that's the seesaw shape, and don't forget your lone pair of electrons, which are critical to assuming this seesaw shape. Just to talk about the polarity of a seesaw, well, in this case you have all your polar bonds are pulling in the same direction. So all pulling in the same direction. You get a net positive charge here, and then your net negative is down here with the fluorine. So you could draw an overall net dipole for the molecule. So the molecule is polar overall. So seesaw molecule is polar. Just to take a look at seesaw then in FET. So if we go to FET here now, when we remove everything, seesaw then has 4 bonds, 2, 3, 4, and a lone pair, and that's your seesaw. So see what this looks like just to visualize it. Does funny things. Let me get it around to the way I want it. So I'm finding it more difficult to manipulate this. That looks pretty good like a seesaw actually. So there's your 2 legs, 2 fluorines in the bottom. This is the seat of the seesaw, and there's your lone pair of electrons at the top. And the bond angles are all 90 degrees there to the central atom. So that's again the use of FET to illustrate these shapes, 3 dimensions. So that's your seesaw. Now the third possible situation we can have for 5 electron clouds around the central atom is going to be 5 electron clouds and 4 atoms. So 5 electron clouds and 4 atoms, a good example would be chlorine trifluoride. So not a common compound that you'd come across, but it does exist. So chlorine trifluoride. So chlorine is at the center in this case. You have it bonded to 1 fluorine here. There's 1 fluorine coming out at you, and then there's another fluorine here, and then you have lone pair of electrons either side of the chlorine. So the chlorine has 2, 4, 6, 8, 10 again, so 10 electrons. It's an expanded octet. Don't forget to put in your lone pairs for your fluorine. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. This particular shape is called a T-shape. T-shape. Now it's called a T-shape because it shapes the letter T. But just to talk about the polarity of the molecule, then if I redraw it over here, so this is my T shape. Don't forget your lone pairs. Right, in terms of polar bonds, there is a polar bond between the chlorine and the fluorine here. There is a polar bond between the chlorine and the fluorine here, and there's a polar bond in this direction. So you still have a center of positivity here, and then all the negative stuff is between the fluorines, and you can draw your net dipole again. So again, T-shape is also polar. If we take a look at the T-shaped molecule, so ClF3 in FET, so in this case we want to just remove everything. For ClF3 we want to put in 3 bonds, 1, 2 and 3, and 2 lone pairs, which gives us our T-shape. And you can see the T has formed quite nicely there. 90-degree bond angle, and that's quite straightforward. Probably easier to see why that molecule is polar there from the FET simulation. Okay, and now for the last, so we're going to have to go on to a new page here just to show the last combination for 5 electron clouds. So if I get a new page, okay, and we're still using our same scenario, so I'll just lay out my table like I had before. Use a thinner line. So that's going to be for my Lewis diagram. This is going to be for the electron clouds, number of electron clouds, and then this is going to be for the shape and polarity. So the final shape for 5 electron clouds is linear, and that's with 3 atoms. And a good example of this is I3 minus. So with I3 minus you have 3 times 7 valence electrons plus 1 from the ion, which gives you a total of 22 valence electrons to arrange in its Lewis diagram. I3 minus is just one of those Lewis diagrams that you'll end up memorizing because it's quite strange. But the central iodine has a total of 3 lone pairs on it. Okay, so a total of 3 lone pairs on it, and again just to illustrate those 5 electron clouds, so there's 1 here, 2, 3, 4 and 5. It has a total of 10 valence electrons. So again, that's an expanded octet situation. Expanded octet, and the shape for this is linear, as I've mentioned already. And with I3 minus, you have your 3 iodines in a row. Don't forget your lone pairs. And this is very much non-polar because none of the actual bonds themselves are polarized, so there's no permanent dipole for any bond, and as a result I3 minus is non-polar. Just quickly throw that into FET, so we remove everything, 1, 2, and then we want to have 3 lone pairs, so 1, 2 and 3, and then you can see how it becomes linear with those 3 lone pairs. So that would be a model for I3 minus, and the bond angle is 180 degrees. So that's everything you want to do with 5 electron clouds. Now we're not just finished with level 3 yet, we need to look at 6 electron clouds. So we'll just extend our table on down a bit, and we're finished with 5 electron clouds there. Okay, so if we now look at 6 electron clouds, so with 6 electron clouds there are only 3 possible shapes that you can have. Okay, so for 6 electron clouds now, there's only 3 shapes that you can have. So the first scenario is 6 electron clouds plus 7 atoms. And a good example of this is SF6, so sulfur hexafluoride. So the Lewis diagram for sulfur hexafluoride is going to involve using 6 valence electrons for sulfur plus 7 by 6 for fluorine, which gives you a total of 48 electrons. And those 48 electrons are arranged in what's called an octahedral shape. So for the octahedrons, just use straight lines. It's for simplicity's sake when you're doing the shapes. Works quite well. No need to use dashes and wedges. So you have your 6 fluorines arranged around the central sulfur. Put your lone pairs on each of the fluorines. Tedious, as I know, but important for determining the shape. 4, 6, 2, 4, 6. Now, the interesting thing here is we now have 12 valence electrons. 12 valence electrons around the central atom. 2, 4, 6, 8, 10, 12, or 6 electron clouds. 12 valence electrons is again an expanded octet. Now this is because of the closeness in energy levels between the 4s orbital and the 3s orbital, or the 3d orbital. So the 3d, remember, can hold up to 10 electrons, and the 4s can hold 2 electrons. So those 2 orbitals would account for the 12 electron capacity of an atom like sulfur, and hence the expanded octet. The shape, as I said, is called an octahedron, or octahedral shape. If you draw it out, so you have your sulfur, fluorine, one at the top, one at the bottom. So if you draw that out, you should be able to roughly see the shape of an octahedron as you join all those points up. And it's an octahedron is a shape with 8 sides to it. So in terms of polarity, hopefully it's straightforward enough to see that an octahedrally shaped molecule will be nonpolar, because although it has 6 different polar bonds, they're all pulling in completely opposite directions, and they're drawing that electron density in completely opposite directions. So the dipoles cancel. There is a symmetric distribution of electron density, just as before. Same arguments we're repeating again and again, therefore it's a non-polar molecule. So an octahedral molecule is non-polar, and if we take a look at that in PhET, we want to remove everything. We want to have 6 bonds and no lone pairs. We just put in 1, 2, 3, 4, 5, and 6, and there's your octahedron. So with an octahedron there, you can see all the bond angles are 90 degrees when everything settles. So the bond angles in the octahedron are 90 degrees, bond angle 90 degrees, and that's your octahedron. So that's the first of the 3 shapes that you can have with 6 electron clouds. So if we just continue our table on down another bit, and we're going to do the final 2 scenarios, and this will complete our video. So for 6 electron cloud, and now for 6 atoms, 6 electron clouds and 6 atoms, an example of this would be iodine pentafluoride, or IF5. And iodine has 7 valence electrons. We have 5 times 7 for the fluorine, so that gives you a grand total of 40 valence electrons. And the shape for this is known as a square-based pyramid. So again, just use straight lines for simplicity's sake here. Don't need to use dashes and wedges. So their square-based pyramid is set up with the 4 fluorines at the bottom, and then the apex of the pyramid is this fluorine up the top. Make sure you put your lone pairs on the fluorines, and you add all those electrons up, you should have a total of 40 accounted for. Again, iodine here has 12 valence electrons, so for the same argument as it was for sulfur, so it has 2, 4, 6, 8, 10, and a lone pair there, which makes 12. So 12 valence electrons, and that's an expanded octet as well. Okay, this shape is a square-based pyramid. Square-based pyramid. Pyramid. And if I just draw that out again to illustrate that shape and the polarity of the molecule, so the square base is set up, as I say, by these 4 fluorines at the bottom, and then the apex of the pyramid is set up by that fluorine at the top. And that's a square-based pyramid. The polarity of this molecule then, if we take a look at the polar bonds, we have a polar bond, 4 polar bonds here at the base of the pyramid pulling in these directions, and then a polar bond up here. So although these dipoles down the bottom cancel each other out, there's still a polarized situation here in the molecule going from iodine to fluorine. So overall there is a net dipole, and so the molecule is polar overall. So not all the dipoles cancel. As a result, you have asymmetric distribution of electron density, and as a result this molecule, a square-based pyramid, is actually polar. So that's a good one to put on exam questions, because it's not that evident initially. So they like putting square-based pyramids on, And then the final shape we can have for 6 electron clouds with 5 atoms is the square planar situation. So an example of this is xenon tetrafluoride. So xenon, although it's a noble gas, it will form this compound. Xenon will have 8 valence electrons, and then fluorine will have 4 times 7, so that is 36 valence electrons. And if you do that out, then the shape is a square in the plane of your page. So just use the straight lines again, and then make sure you put your lone pairs in each of the fluorines. And then the xenon turns out to have 2 lone pairs of its own. And so the xenon in this case has an expanded octet as well, 2, 4, 6, 8, 10, 12. So 12 electrons there, 12 valence electrons as well for xenon. The shape here is square planar. And if we draw that shape out, so xenon and 4 fluorines in the plane of the page. Okay, well in this case all the dipoles are pulling in opposite directions, so they do cancel each other out, so this is non-polar. Now just to finish off there, I needed to do the square base pyramid in PhET, so I'll do that first of all. So remove everything. Square base pyramid has 1, 2, 3, 4, 5 bonds in one lone pair, so 1, 2, 3, 4 and 5, then your lone pair. And there's a square base pyramid, or square pyramidal, as this piece of software is referring to it as. So there's a square base pyramid with your lone pair of electrons, and all the bond angles are 90 degrees, so that's easy to see there. And then if we're going to do our square planar, well, we remove one of the bonds there and we add another lone pair, and there's a square planar, and again 90 degree bond angles, and that would be xenon tetrafluoride. So in terms of Lewis diagrams and shapes for level 3 molecules, that is the best video I can cover for that one. Any questions, just post them on the video and I'll try to get back to you on those. But that is a pretty comprehensive overview of the shapes, how to draw Lewis diagrams, and how to determine whether the molecules are polar or non-polar.